the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Is actually one that I think summarizes pretty much a lot of the technology that we've been developing, a lot of the background of myself, my co-founder Edie and Lou, and our whole team, as well as the directions where our technology is taking us currently. I think it's usually going to be, it's typically a shorter presentation that I'm used to taking. So usually one's around 10 to 20 minutes, not as long as this one. So this actually gives me a unique opportunity to really explain actually a lot more than I normally do about how the technology works, as well as the origin of the tech. But essentially, what we're really trying to do at PolyGone isn't just create like a solution that's very focused on one specific area. This is actually designed to be a very scalable solution. So we call it the first systematic solution to microplastic pollution, because there actually are several other technologies being developed simultaneously to ours that are able to address microplastics quite effectively, but none of them are really able to address the broader scale of the problem because, as I'm sure many of you know, microplastics are a global problem. They're everywhere. And they're things that are very difficult to conventionally remove, especially in things like open channel environments. So as a quick primer, I know we already had a little bit of an introduction on what microplastics really are, but they're essentially any plastic particle, piece, fragment, fiber smaller than 5 millimeters in size. Now, this is actually a very broad range because 5 millimeters is actually quite large, and then you can go all the way down to the nanoscale, which are definitely in the scale where they're microscopic. You can't really detect them very easily, let alone remove them. So treatment techniques needed to remove things near the 5 millimeter size are actually very different from those that need to be treating things at around a micron in size or smaller. But generally, these are things which you can see in this image here are all examples of different types of microplastics. These are fibers, fragments, pellets, films, and many of them are actually produced as microplastics. So these are things like anything used in a lot of exfoliants, things that are used as pellets for production. Nurdles, for example, these are all different types of plastics that actually are produced to be in that microplastic size. But the vast majority of microplastics are actually shedded from other things. So these are things like fragments from car tires that wear away over time, fibers from your clothing that shed and wash away during wash cycles. So there's a wide variety of different sources, even things like paints that get applied to buildings that eventually chip and shed are classified as microplastics. So these are sourced from all over, and that leads to them becoming a global problem. This means that they're not localized. So these are things that, unlike with a lot of conventional waste, where it's really limited to specific sites, like there's been an emission point and then it all deposits locally, we're finding microplastics everywhere. They've been identified in over 93% of all bottled water sources. In fact, every time you actually drink a plastic bottle of water, there are nanoplastics that are inside that are being emitted largely from UV degradation. So plastics, when they get exposed to sunlight, the UV from that causes them to start shedding very small nanoplastics into bottles of water that can get as high as 250,000 nanoplastics per bottle. So if there's one recommendation in terms of habit change, I would definitely recommend people, if they can, try and reduce the number of plastic bottles they're drinking from if they want to reduce the amount of microplastic or nanoplastic in this case that they're being exposed to. But they've also been identified in 100% of the world's oceans and lakes. This is something that's very alarming, especially for anyone that's interested in marine ecology. These things are easily ingested by plankton that then it gets bioaccumulated up the food chain. So we're finding higher concentrations of microplastics in predatory fish than what we're actually finding in lower down in the food chain. And the predatory fish are actually the fish that we usually tend to eat the most of. So it ends up getting into our own diets. And then lastly, the thing that's actually alarming people the most now is actually the deposition of microplastics, specifically the smaller ones in our brain, lungs, blood, testicles, and other bodily tissues. This is because when plastics are at the larger size and we ingest them, so if we're ingesting larger scale microplastics, they tend to go right through your digestive tracts, don't really interact with your body too much and flow right out. But what we're finding is that as plastics get closer to that nanoscale, when they're really around a micron or just above a micron in size, going down below, we're finding that they're able to actually pass through the digestive tracts into the body and then actually even pass between the blood-brain barrier. This allows for very high levels of deposition compared to what we originally thought would be the case for microplastics. And alarmingly, we're finding concentrations on the rise. So we're seeing that in samples taken from bodily tissues from 2016 versus 2022, we're finding in some cases as much as a 50% increase in levels of microplastic presence in these bodily tissues. So this is becoming something where it's very much an emerging problem. The amount of microplastic we're exposed to in our daily lives is going up and up and up. And that's leading to greater amounts of ingestion and then greater amounts of deposition into our bodies. And the reason this is something that a lot of the scientific community are worried about are the additives in plastics. So it's still currently up for debate exactly how harmful microplastics are. And the reason being is actually no plastic is really the same. So every single plastic item has different kinds of coloring agents, different chemical compositions, different other additives, like some contain flame retardants, some contain other agents that are very toxic. But many of the agents that are added into plastics are carcinogenic, endocrine disrupting, and neurotoxic. Specifically things like phthalates, BPAs, all of those kinds of chemicals. And what we're finding is that in the smaller plastics, so the ones that are more degraded, things at the nanoscale, not only are they easier to deposit in your body, but because they're less stable, they're more likely to leach the chemicals that are within them into bodily tissue. So we're finding an annoying, very frustrating combination where you're getting a higher deposition of these smaller particles in bodily tissues, and these smaller particles are more likely to leach harmful chemicals. So it's really becoming a big concern within the scientific community on how we can actually start removing specifically the smallest types of microplastic, because they're the ones that are more likely to pose a health hazard for the next generation. So when Edian and myself started our research at Princeton, we were both, I was introduced, we were both studying architecture, actually. So we didn't come from a material science, chemistry, or environmental science background. But what my focus was, actually, when I was designing a lot of structures, was on infrastructure. So I was designing, for example, I was on the design team for the super trees in Singapore, as well as several large-scale utility designs. And I wanted to see if we could apply design thinking to address gaps in waste infrastructure. So when I went to Princeton, actually, my first focus wasn't really on microplastic. It was on plastics generally. We were trying to see how can we take waste management and redesign it in a way so it can really address a lot of gaps. So we wanted to see where are the gaps currently in treatment and collection and concentration of waste, and ultimately recycling of waste, and how can we start plugging those gaps? And the reason why microplastic became something of such strong interest to myself and my co-founder is that there really weren't any systems out there specifically to capture microplastics once they enter our environment. You have systems designed for larger scale waste. They're not really managed very well in many cases, but they do at least exist. For microplastics, there's very limited options. So for things like rivers, reservoirs, ports, open channels, they don't really deal with the vast majority of microplastics, any systems that have been put in. So typically what's done there, so if you're in a river, ports, those kind of environments, they deploy what are known as trash trappers. These are usually these big collection chambers that they just position on like a river, and they have a series of meshes in them to really intercept different sizes of waste. But there is a threshold there, because the more fine you make the meshes to capture waste, the more bycatch you get. So you end up catching fish, you end up catching natural debris like leaves and twigs, things you don't really want to be removing from things like rivers, streams, reservoirs. So there's really a hard limit on what you can really filter using conventional techniques here. So these are very effective at capturing things like plastic bags, plastic bottles, larger waste. But when it comes to things below 5 millimeters in size, and specifically below around 2 millimeters in size, the vast majority of these systems tend to fail. So you're able to get very effective filtration down to a limit, but the vast majority of these microcontaminants evade treatment. So there's really not anything for these open channel environments that are available. Now, when it comes to water treatment, there are actual systems in place that can deal with microplastics. These are ultrafiltration or tertiary filtration techniques. Most notable ones include things like granular activated carbon filters or reverse osmosis filters. These really are very effective at capturing almost all contaminants. The challenge is actually in scaling these solutions broadly because they're incredibly expensive to install and maintain, and they're also incredibly energy intensive. So when we were doing our research, we started studying what is currently used in water treatments, and in around 70%, just under 70% of water treatment facilities in the US, they don't really employ extensive ultrafiltration, RO, and granular activated carbon systems. And the reason is they're very impractical to install. So a lot of the infrastructure that's been built, especially in America, is actually fairly old. And to actually add in something like an RO system for a large municipal treatment body, you need to actually siphon all of the water that's going to be going out of the facility and run it through a series of these membranes. And each of these membranes, as its reverse osmosis, is actually very challenging to push water through. You need to really aggressively pump the water through the membrane in order for everything to get filtered through effectively. And to do that requires intense pumping, and that requires intense energy. So these things are oftentimes facilities that cost millions and millions of dollars to add on to existing infrastructure. And once they're onboarded into the infrastructure, they actually require millions of dollars to maintain, just largely because of the energy use and how frequently you need to swap out the membrane systems. This means that they're very effective for very affluent areas, which have large budgets, but in areas that are very strained and don't have access to extensive support systems, these are really not very practical because all they'll end up doing is increasing everyone's water bill to really install at a widespread level. So there's really a limit in terms of what can be applied inside these water treatment systems. And then lastly, one thing I'd like to mention is that while these filters are able to effectively remove microplastics from treated water, what ends up happening in the actual treatment process is the water goes in, all the stuff deposits on the media, and then they eject it back out into the source. So every bit of microplastic that was in the source water actually gets re-ejected back out into the source. So you're not actually removing microplastics from the environment, you're just filtering it out from your drinking water. So these are things that are effective at filtering water, but they don't actually solve the root problem of actually removing microplastics that have already entered the environment. So this problem really inspired my co-founder and I to really develop what we consider to be like a completely new type of filtration specifically targeted towards removing microplastics. What happened actually when we were at Princeton was we were very much discouraged from pursuing this research, actually. So when we started out, we were originally looking into broader plastics, but when we pivoted to microplastic, the first thing our advisors told us were that this is too big of a problem to really deal with. This is something that is a global problem. We do not have the expertise to deal with this problem. We're designers, we're not material scientists, we're not engineers per se. And they wanted it to be really solved by other people. So they said, essentially, this research is going to be a waste of your time. And both Idian and myself, when we heard that from our first review, we were a little bit discouraged, but ultimately we're very stubborn people. And we acknowledge that we actually don't have the expertise to solve this problem on our own. And that really inspired us actually to connect with people from outside our department to see if we can co-develop a solution to address microplastics. So that's where we connected with Dr. Ye Yao, who was a PhD in chemistry. And we asked, hey, we have this idea that we want to test for seeing if we can remove microplastics from water. We have some rudimentary ideas. Are these worth testing? And we got a lot of support actually from both her and her advisor, actually, who was Professor Tai Sok Moon. to sort of co-develop a solution. And how we started actually analyzing what kind of solution would work is we turned to not exactly what's currently used in filtration technology. We didn't really want to make an incremental change to what's currently there, like not a slightly more refined RO system. Instead, we actually looked into where were microplastics depositing in nature? Where were they ending up? And what we found is there was a very unique plant that was accidentally capturing a huge amount of aquatic microplastics. And as it happened, Dr. Yehu was actually doing a study on that specific plant species. It was a type of water lettuce, and what it has is these very fibrous roots that go into the water. So it just floats on the surface, the roots go in the water, and passively it was capturing really high quantities of microplastic in contaminated environments. So that really got us wondering, why is that the case? What properties of these roots are actually causing it to capture microplastic? So we did a study with their research team, and what we found was the plant roots themselves were very hydrophobic. So they actually produced a gel on the outside of the root. It's called a plant root exudate, and it's ultra hydrophobic. So it really wants to repel or reduce its contact area with water. And what we found is that the vast majority of plastics are also very hydrophobic. So if you put these two materials next to each other, they just passively stick to one another. So in gravity flow, a small plastic will run past the root system, and like a feather duster, it'll just get attached. And that's a really interesting mechanism that we thought we could see if we could replicate. So our first idea was, why don't we just take these plants, create wetland pads out of them, and start deploying them for water treatment? And we thought it was a great idea, but what turns out happens is as soon as you put it in a very contaminated environment, these plants die. They also form habitats. These things are very easy for colonization, especially by small aquatic life forms. So we're actually bringing life forms closer to where the microplastic is, which is not what we wanted to do. And then lastly, we were finding that these plants are actually considered an invasive species in much of the US and much of the broader world. So if we were to start using them and they were to start leaching out and expanding, this could pose another ecological risk. So we couldn't really deploy the plants as they were. So our next plan was, how can we create a material or create some kind of filter media that emulates the properties of these plants so that it can effectively treat water in the same mechanism? And that's really where we started off on, and we've been working on it for a couple of years. We managed to onboard a series of engineers now to help us build our broader systems. And we've also been getting a lot of additional advisors, notably Nicolette Van Etzel from SAP, who's really helping us expand our commercial operations. And in terms of what we've developed, so the ultimate solution that we've developed so far is a modified silicon. So just like what we were doing with these plant roots, we were trying to leverage the hydrophobic nature of the material. And we're also trying to leverage the very high surface area that fibrous plant roots had by creating these very long, thin strands of the material. So what we've done is really just translated the morphology and the chemical composition of the plant root exudate into a material that can be synthesized and can be scaled and deployed in industrial environments as well as in open channel environments. So that's actually the core innovation that we've developed. The cool thing about it, among many things, is that it's completely passive in how it filters. So if you put this in a treatment facility, you don't need to run aggressive pumping to really get water to aggressively force the plastics onto a membrane. This thing really works in gravity flow. Just as long as there's a slow flow going through, we can actually have all the plastics, around 98% of sub-millimeter microplastics, sticking to our filter media down to around a micron in size. And this gives us several competitive advantages. So compared to RO, or granular activated carbon, if we were to make a municipal scale system like this one on the right, we're actually able to do it at around 10 times less of the cost, or 1/10 the cost of those competing systems. The system as well is completely mechanical in how it filters. It's not emitting any chemicals, so there's no risk of any downstream effects from actually putting the media into the water. The media itself is also 100% recyclable. So at its end of life, you can just take the silicon, send it off to a silicon recycler. And we have a partnership actually in Fort Lee for that. And it can be reconstituted into silicon oil and then reconstituted again into the filter media. So we can actually regenerate the media long term and reuse it. And then on a daily basis, you can actually wash this filter media. So what this system on the right actually does is it introduces a big box of our filter media into the effluent. So this is the effluent from actually a facility we're working with in Atlantic City. So they have the effluent flowing out into this big, what's called an EQ basin. We introduce a box of our filter media into that lake, into that outflow into the lake. It intercepts the microplastics, and then when it saturates, you can just take it up very quickly, aggressively wash it using our patented wash system. And that takes around 1 minute to wash around 96% of anything that's on the feed filter media right off. We then evaporate that concentrate, and then we get basically a dry sample of microplastic that we've extracted from the effluents, and then you can reintroduce the filter media for continuous use. So this is actually the system we're building out right now for Atlantic City as one of our first commercial deployments. And it's allowing us to not only filter out any microplastics that are evading their existing treatment processes, but we're for the first time really able to recover microplastics at scale. And that's really important for us because our end goal ultimately isn't just to remove these microplastics, but to ultimately recycle, upcycle, and create a circular economy out of this rather than something that would just be burned, destroyed, or emitted back out into the ocean. So we're really proud of where this tech development is leading us at this point. So what we're finding at the moment from our market interest is there's two different types of systems that we are really focusing to address. Like there's big treatment systems that have to deal with huge amounts of water. So these are municipal scale systems. These typically deal with between, on the low end, around 1 million gallons a day, and on the high end, up to 100 million or 150 million gallons per day. So we're finding the average facility really uses around 10 million gallons, goes to around 10 million gallons per day. So we designed our first municipal system, which are these polypod systems, to really deal with that threshold. So these individual systems, each one costs around $300,000 in total and can treat 10 million gallons of water daily using our filter media. So in this system here in Atlantic City, they typically have around 20 million gallons a day going through their facility. So we have two of our polypod systems really to address their effluent. And then what we're also finding is there's actually a huge number of smaller treatment facilities. And this is both in municipal, but also private sector treatment. And in those cases, they're not really dealing with millions of gallons per day, but they might be dealing with 10,000 to at most 100,000 gallons per day. But what is unique in their cases is that they're almost exclusively inline systems. It's almost always closed piping. They don't have any open channels where we can introduce a large box of our media. So what we're developing for them is what we call the poly cartridge, which is basically a cartridge filter filled with our media that we can then backwash, recover the plastic from it, and continually use there. So we're developing these two systems simultaneously. And one of the core things we've learned through our experience trying to deploy and get these things sold is basically one of the things that everyone cares about is how easy these things are to install and how easy they are to maintain. No one wants something that they have to deal with multiple times a day or spend hours on a day. And they don't want to have something that takes ages to install, like a month to install or anything like that. So both of these systems are designed to be installed in as short as a day. So this is one of the cool things about our system. Our polypod can literally be shipped over to the site, placed, and it only requires a single standard electrical outlet and a standard hose inlet to function. And the poly cartridge can be just shipped it's around just over a meter tall, the actual full-size system, and it can really be transported very easily and installed just in an inline, plug in one pipe in one end, one at the other, installed in as little as an hour. So that's one of the big targets for our team, is trying to see how we can make these things as easy to install, easy to use as possible for operators. And then in terms of the performance of our systems, we're really getting quite good results now. So this is something that actually changed a lot over the R&D. When we did our first ever system, we were getting around 25% removal, which is pretty bad, but it's a starting point. And that's when we were like, okay, it's not perfect, but what are the mechanisms that are working with it? And then we really worked on optimizing it, incrementally improving the media again and again and again. And we're probably now at around our 50th formulation. And we're now getting consistently around 98 to 99% microplastic removal across almost all types of plastic. So we're really excited with that because that compares pretty similarly to reverse osmosis, but at a fraction of the cost, a fraction of the energy, and yeah, basically a fraction of the cost per kilogram removed. So this is really what we're trying to go with, is trying to see how can we make a substantial advantage over existing systems specifically for microplastic. So now where we are in the business, we offer sort of three key services, all of which are sort of targeting different sectors. So we've got the municipal treatment arm, the industrial treatment arm, and then a third arm that we're finding is actually surprisingly popular at this point is actually lab analysis, where data is becoming very important for every single group. Like all of these groups, especially in the private sector, they want data on what they actually have in their water and how much we can remove so that they can actually publish reductions, removal, efficiency, and all of those things that can keep either regulators happy or shareholders happy. And this is something that is really this year, at least for our company, being the fastest growing part of the business is actually the data reports that we're actually producing from our pilot deployments. And I can go into that in a little bit. But ultimately, before I go into that, I'll explain these were our first ever deployments. This was back when we were getting like reasonably high efficiencies. I think this one here is an image of our actual 98% lab efficiency. So you can see a brush made of our filter media here in this image on the left. All of these glowing particles here are literal microplastics. So we had a tub filled with loads of these fluorescing microplastics. The big ones, these orange ones, are around 500 microns, or half a millimeter in size. And these small little yellow ones are around 100 micron in size. And when you put the brush in, it just all scoop them all up and started sticking. And then after around 2 minutes of exposure, in this case, we were getting around 98% capture efficiency. So the entire tank was pretty much cleaned. And then our second test we did before we started doing our large scale operations was there was a contaminated lake in Canada, a very, very contaminated lake in Canada. And the reason why it was contaminated is largely because we didn't know, as the scientific community didn't know how dangerous microplastics were. So they wanted to do a test to see if we introduce microplastics to a pristine lake, what would happen to it? And just so you know, I wasn't part of this study. I think it's actually a very unethical study. But this was done at the experimental lakes area in Canada, where they dumped around 15 billion microplastics every 2 weeks for 3 years into a lake. And the results were that, yeah, it damages a lot of stuff if you add a lot of microplastics to a pristine lake. But they approached us saying, hey, we've got this incredibly contaminated lake now. We need to clean it up. Can we use your technology to start cleaning up this lake? So this actually became our first ever pilot of our technology, was creating what we called the plastic hunter, but we're now considering more like the reservoir Roomba, where we just take basically a floating platform and move it around this lake to sort of skim off any microplastics using our filter media. And we did a small study just over a year ago where we did 40 filters in this pontoon. We didn't even move it. We just placed it in the water. And then within a couple of hours, we'd removed around 500,000 microplastics from just its surrounding vicinity. So that was for us a really good first test to say, all right, the filter media kind of works even in static water fairly well. And we're contracted with them to actually start cleaning up the lake. So we're building an autonomous system right now that's going to go basically back and forth along this lake for the next few years and slowly clean it up. So that's the first ever deployment of our system, and it was a really good proof of concept. And then we scaled up from there. So the next big system was really trying to see, can we remove stuff from municipal scale water? And this was kind of a funny collaboration because when we started, we thought there would be a lot of interest in removing microplastics from wastewater. We're like, all right, we've developed this filter. We see in the lab it's working very well. Everyone seems to be concerned about microplastics, so I'm sure facilities will want to test it out. And we were completely wrong. As soon as we started asking people, hey, do you want to test this? We usually got no response, and in other cases got no's. We actually had over 100 attempts at trying to connect with facilities, and none of them agreed until this one. And this is why it's actually very important to find the right pilot partners, because if you have really good supportive pilot partners, it really not only allows you to test your technology, it allows you to evolve it into something far more than it was to begin with. And this is our experience with Atlantic County. So they were a far bigger facility than we were hoping to get. So we were actually looking to treat things around the 1 million-gallon mark. But this facility actually is 40 million gallon capacity, but generally around 20 million gallon per day capacity, which is far higher than we were expecting. But the key thing is the facility managers were very excited about the project. We showed them our technology, which was quite basic at the time. And the first thing they said is like, all right, let's identify where the best location to test this thing would be. And they really helped us identify the perfect location, which is at the end of their secondary treatments. And that's largely because it doesn't interfere with their existing processes, but it really acts as a finishing filter that really removes anything their current treatment systems don't address. So in this image here, you can see this is their pump house. It's the last bit of filtration after sedimentation and flocculation and all that. And then all of that water flows out of that pump house into this big lake and then back out of this lake into the Atlantic City coastline. So after this point, there really is no treatments. Anything that would be entering this lake will be actually entering into the Atlantic Ocean. So the first thing we did was we took samples from it and we found that there were quite a few hundred microplastics per liter still evading their treatment. And the majority of them were really small ones. These are the ones around the micron size. So the bigger ones were being removed, the denser ones were being removed, but the low density ones that sort of were near the surface of the water, and also the ones that were the smallest, really were still evading a lot of their treatment processes. So that's why we decided, let's see if we can design a system that really skims that outflow to capture the vast majority of what's evading it. And I think this is a short video. I don't know if it'll play well, but this is, yeah, what we were building. Let me see if I can skip past. There we go. So ultimately, that was showing some of the work in progress, but there were two components to this pilot. So there was the main system itself, which is basically a giant skimmer. So we put all of our filter media, we formulated into a brush form, and then we basically got around 720 of those brushes along two sets of trays. One tray would be in the water to basically intercept any microplastics outflowing from the facility. Another one would be raised out for cleaning, and then every few hours it would swap. So basically, these things swap in and out of the water and continuously filter the water whilst being cleaned. This was very much a research pilot, so we were really trying to figure out what were the components needed for this thing to really clean the water. How would we clean the filters? How would we reintroduce them? So it was a very intensive system. So in this case, we had these smaller trays that could be removed. You can see kind of behind this array here, you have what are called wash tanks. So they're these big tubs filled with water and a small amount of detergent. And we basically aggressively shake the filters in that tub, and all of the plastic comes off of them, and then we put them back onto the system. But it was a very manual process. So this is something we needed a lot of support from the facility managers to make sure that there were operators willing to do this. And they were absolutely fantastic to work with. I'm really glad to say they've been a huge support. And we collected data really on like what were their feedbacks, what were the things they thought were the most difficult to deal with, what were the problems of the system, what bits weren't being addressed with the system effectively. So that way we could incrementally optimize how the system performed. And behind it here, what you can't quite see too well, but is an educational pavilion. And this was kind of our way of giving back to the facility, because we noticed that what the facility really wanted, because microplastics aren't really regulated yet, there's no real mandate for them to install a system like this. They want to be seen as something that's innovative, like some group that's really bringing innovation to Atlantic City. And we decided the best way of actually helping them is actually for their tours. So they have school tours, they have college tours, lots of tour groups visiting the facility every week. And we built this pavilion behind that explains basically what microplastics are, the technology we're developing, how habit change can reduce microplastics from entering the environment from the beginning, as well as what the pilot is and how it works. So this actually gave them a really interesting sort of space where they can bring people over to actually view the pilot, understand it, and learn more about what microplastics are. So they've been very happy with that. So you can kind of see here, like this is like the people that were watching on the opening day. It was originally meant for K through 12 students, but we got a lot of adults very much interested in learning about what microplastics are, all the kinds of the ways we're dealing with it, and so forth. And then I can quickly go through the data that we collected from this pilot. So this one was our first major pilot to see, how effective was the media performing at scale. And what we saw was significant fluctuations in how much microplastic we were collecting. And the reason being is actually based largely on what's coming into the facility. So some days that facility was getting water that was more industrial, some were getting more residential effluent, some were having ones with a lot of clothing fibers, other ones were just not. So from a day-to-day basis, we were finding huge fluctuations in the quantity of microplastic that was actually going through our system. But the performance of the system itself was generally pretty uniform. The one thing we realized that was a serious fault in our system with our first ever deployment was actually we underestimated how much microplastic was actually evading treatment, because when we were doing our first samples, we just took a jug of water, but that was an instantive sample. That was the amount of microplastic in that water at that specific time. And as it turns out, when we took that sample, it was actually on one of the low days. It was probably similar to week 5, where we were getting low quantities of microplastic in that instantive sample. So when we based our modeling on how often the filters would need to be cleaned, we underestimated it. So realistically, we were cleaning them once a week originally, and then we've now had to do it 3-4 times a day to realistically get around a 96-98% continuous removal. We need to clean these things a lot more frequently. And that meant that we had to redesign the system ultimately, because that's too much maintenance for a single operator to really constantly be at this thing, removing, cleaning, and replacing filters. But in terms of the kinds we were getting, these are some images of the different kinds of scales we're getting at. So some of them are fairly large. You're getting these films and fibers, which are around 300 to 400 microns, so around half a millimeter in size. But the vast majority of what we were getting were these very small pellets and fragments, quite often around a micron in size. So really small ones that were evading their existing treatment systems. And yeah, you can kind of see here the vast majority, in this case, were particles even. So ones which were really around that exact micron. And yeah, in this case, we were doing analysis. So we took samples on from the brushes, also ahead of the system, behind the system, to assess the performance of the system. And in all cases, all these fluorescing dots were from our analysis protocol, where we take these samples, apply a Nile red staining dye to them, and then analyze it under a microscope. And the microplastics themselves, depending on their composition, will fluoresce at different wavelengths we analyze it under. So we started by doing this method of analysis, and now we've actually upgraded to FTIR and pyrolysis GCMS, which are far more intensive methods of analyzing the very small microplastics. So these are better for analyzing the ones closer to that micron in size. And what we're finding is a very sort of standard bell curve in terms, not bell curve, sorry, exponent curve, where we're seeing like the vast majority of what we're able to collect with our media is really the smaller plastics. So these are ones that are, once again, close to that micron in size. But then we were also finding it actually rising a little bit, which is what we weren't expecting, were actually some of the very large microplastics. So the very large ones, which are actually visible to the naked eye, we were also able to capture as well. And then lastly, we got actually a lot of really interesting media support for this pilot. This is something where we were actually surprised by the amount of public interest in understanding this problem and trying to have systems to remove it. And that really is a good precursor or foreshadowing to actually what has happened more recently with our business. But we were very surprised. We actually were featured on PBS News. We got in a bunch of articles. We got a proclamation from a New Jersey senator. We got a lot of support for this. So we were very happy about the amount of media coverage and the amount of public support, both locally and a bit further afield, to actually see systems developing for microplastic removal. And that sort of led into a lot of our subsequent pilot work. And ultimately, I don't know why the font's seemingly going a bit weird, but essentially what we've had since then is an interest from the facility to actually do a commercial pilot system. So the facility, once again, was very supportive of the work we were doing, but they were also very happy with the preliminary data and also happy to work with us. And I think that's largely something that's missed a lot in a lot of engineering and science related work. Is actually it's very much dealing with people. And I think we had a very good relationship with both the facility managers and the operators, and we took their feedback into the design of this new system, which is essentially the same thing. But what we've done is we've identified key faults in the existing system. So the one that's out there is very much exposed to the elements. We found birds nesting on top of it. We had huge amounts of rain and things interfering with our filter media. So now the entire system is for the most part enclosed. So we have this big box. Inside that, we have our filter media that gets raised and lowered into the effluent stream at very controlled times. And once again, to deal with that issue of continuous cleaning and removing and reinserting the system, it's now an entirely robotic system. So we're actually robotically raising, lowering, and cleaning the system in an automated way. And what happens is the concentrate from this tub gets evaporated, so they have to deal with far less water than before. And that water evaporated concentrate really goes into these small little chambers on the outside of the system that an operator can just pick up and then ship to us. And that way, we're actually able to handle the waste without it using up really any time for the operator. So the aim is really to have this thing have around a 10 to 15-minute interaction from an operator per week. That way, we can actually make it something that is easy for them to use and not really a bother for them, and also very effective at dealing with microplastic. And so they've actually decided to foot the bill for this. So they're working with us for a $900,000 deployment of a system. But once again, it sounds like a lot of money, but at the same time, we're treating water for over 200,000 households. So this is, once again, a 20 million gallon per day capacity. An alternative system at this kind of scale typically would cost between 3 to 20 million to really install. So we're quite happy with being able to get the cost down quite dramatically over alternative systems. And then since then, we've actually had a lot of interest from private sector. And this is something that's really actually only occurred in the last 5 months. So this case study here is a group called Way Out Water. They're actually producing drinking water systems, and they're designed to fit in shipping containers. So they have these big shipping containers. It has inside it every single type of treatment system. So you can basically plug in a hose with any kind of standard water on one end, and drinking water comes out the other end. And they really wanted to connect with us largely because what they wanted to do was remove any microplastic from the inflow of their system. And the reason being is that although they can already filter out microplastics, the ones that were actually getting through their system were, one, clogging up their ROs. So they had reverse osmosis and it was getting clogged because of the high loads that were going in. And secondly, as I mentioned before, when the RO gets discharged, it actually just discharges the microplastics back out into the source water. So it doesn't remove it from the environment. They wanted to see if they could implement a cartridge version of our filter to actually improve the environments that actually they're sourcing their water from. And that could be a really interesting value add for their business. So they've partnered with us. This was a system we deployed actually just a couple of weeks ago in Dubai, and we're really seeing how well it performs right now. But this is designed to treat quite a large amount of water as well. I mean, it's around 5,000 gallons per day, but that's really meant to treat like supply drinking water, especially in the Middle East, for at least a couple thousand people. And then additionally, we've had more recent municipal contracts. So another polypod system is being requested from West County Wastewater District. This is in California, so other end of the country. And this one they want to get deployed in summer next year. So in that case, we're doing a very similar system. So this is another 10 million gallon per day system. We only need one of our polypods there, and we're going to be placing it on top of their partial flume to once again intercept anything that's currently evading their existing treatment systems. And then lastly, in terms of a really interesting area for us, is actually microplastic analysis and certification. And this has been something that's taken off really in the last 2-3 months. But we've got a really good analysis lab now, largely because we wanted to prove our system worked. So we developed and purchased a lot of high-end equipment. So we got our own pyrolysis GCMS, we've got access to Princeton's FTIR machine, and we have our own Nile red staining protocol. And that really gives us around the most accurate testing you can really do for microplastics anywhere. And we've been actually approached recently by both individuals and companies wanting to test their water and their products, because a lot of people want to say that they've got microplastic-free products, but a lot of it is greenwashing, and they want to have real certifications to prove our product is different from all these greenwash companies. We've actually been third-party tested. So we're actually doing third-party tests for a few companies right now. This is one we just completed for a microplastic-free tea bag. So they're trying to use completely non-synthetic fibers for their tea bag. And they scored pretty well. We did a test for them. We dunked the tea bag in the water. We tested it multiple times, and we found negligible microplastic emissions. We did find some cotton emissions from there, which we did notify them of, but we didn't find any microplastics coming out of their tea bag. So that was an example of one that's gone very smoothly. But we're getting a lot of interest from also drinking water companies. they're very interested in like showing that they're actually doing proper filtration for that water. So even if they have existing treatment, they want to make sure that they can prove it. So that's where we're really working with those groups. And then actually, lastly, for the West County Wastewater District, how this one is being funded is very unique. So we actually got sponsored by Amazon to do this one. And that's a very unusual thing because when we were actually talking with them originally, they wanted to see if they could sponsor this project. We wanted to know why on earth would you want to sponsor this? I don't think you've really got anything to do with this specific water treatment facility or really microplastics generally. And what we found is that they are in a very precarious position because they're building loads and loads of data centers at the moment, and data centers use a huge amount of water and are incredibly damaging to watersheds. So what they need to do in order to actually get approvals for these data centers to be built these days, they actually need to provide evidence that they are going to be maintaining access to water and also improving water quality wherever they're deploying their data centers. So our system actually aligned quite well with that second metric of improving water quality. So they actually want to have the data saying, look, we sponsored a system here. It's removing X amounts of microplastic for this many households in this district. So what we're trying to do actually with this is see how can we leverage these private sector partnerships to launch systems to remove microplastics in a pre-regulatory environment. So it's a really interesting opportunity where we have to really carefully align sort of the political interests of all these different companies in order to actually create impact. And it's been a real difficult thing to do, but we're actually getting some headway with it. So I'm really excited about this project launching specifically for that purpose. But it's really highlighting as well that data is going to be incredibly important for actually getting our technology deployed widely. So this is why the lab is becoming a really interesting part of our business development. So in terms of our existing partnerships in the private sector, this is a list of the different groups we're now working with. And I can quickly go through why, because I think I explained Amazon, but the majority of these you probably don't know. Vibrant is an example of one of those drinking water suppliers. They're trying to really market themselves as having microplastic-free drinking water. They're using glass containers for all of their water. They're using the most state-of-the-art treatment systems. We're going to be doing regular reporting for them to show, all right, are you actually producing microplastic-free water? And if they are, we'll provide them with a certification. If not, we're not going to provide it. Kurita is a Japanese industrial water treatment provider. So they actually work with a whole variety of different things like heat exchangers, cooling towers, and all of the piping in those systems. A lot of them are made of PVC. So they're very worried about PVC buildup in all these recirculating water systems, not just for contamination purposes, but actually because that will actually reduce the efficacy of cooling a lot of these industrial systems. So they want to see, can we remove any of these microplastics that would otherwise be building up in recycled water systems? ACUA is our partner for our main water treatment that I've shown already. But the more interesting sector that I think is going to be the growth sector for our business is actually going to be H&M, Lululemon, and Nike are. So they're all in the textile space. And similarly to what we had with Amazon, they actually approached us and asked, hey, do you have a system to remove microfibers, which is a subcategory of microplastic from water? And our first question to them is, why do you want to remove that now? Like, we want to remove it, but why would you want to remove it? Because there's no regulation yet. And it actually turns out it's quite interesting that basically in the EU, they had a mandate in certain states that you have to remove microfibers from washing machines. And this is really for domestic washing machines. So if you have a washing machine and you're in France, you need to have a microfiber filter in your washing machine. And what's interesting is that actually got all these big companies panicking because they're saying, all right, regulation is happening on these small washing machines. It's only a matter of time before that extends to large washing machines. And all of these companies have giant washing facilities where they're producing all of their clothing. And they have positioned them all in Asia where there's minimal regulation. So they are just dumping huge amounts of microfibers at the moment into sewer lines that go out into the ocean with pretty much no treatment at all. But as a result of this EU regulation, they're going to actually have to start reporting all of their global operation emissions. And so they're under extreme panic now to start putting in systems to start removing all of these microfibers that are currently being emitted from their facilities. So we're at an interesting point now where we're actually doing trials with H&M, Lululemon, and Nike all at the same time because they're all in a desperate need to start actually removing these things. And it's a very scalable model. So unlike with water treatment at a municipal level, where it's a big contract, but it's 2 years or so before you get anything signed on, these groups are happy to sign on within a couple of months. And then on top of that, it's not just one facility, they'll have 20 facilities or 100 facilities, or in the case of Nike, around 2,000 facilities they work with. So there's a huge scalable opportunity to start actually getting huge amounts of impacts in removing microplastics at scale using this new development in the regulation on textile spaces. And it's our anticipation that this kind of regulatory frameworks are not just going to be happening in the textile space, but ultimately in things like the consumer packaged goods spaces as well, which is an even bigger, broader market, and eventually in municipal treatment. But my assumption actually at this point, and I can go into that in the Q&A, is I think municipal treatment might be one of the last areas to properly regulate for microplastic, largely just because of the complexity in establishing a regulatory driver for it. But I think ultimately municipal treatment will be the biggest market, but we're seeing that as our end market for something really in terms of growth. So I can quickly go through like how we scale our systems within all of these different groups that we're working with. So
Hey,
what they're
Nathaniel, we have just 2 minutes left.
Oh, geez. All right. I actually went over time. All right, that's great. All right. Well, I'm at the very end. So generally, how we scale it is we do bench studies just to really test, does our system work? If it works, we do integration. That's really to see, do we damage any of their existing systems? If we don't, we reach their KPIs, and then we do a full commercial system, and then that networks out. And then lastly, just where we are, a lot of impacts, lots of awards. We're doing pretty well on that front. Lots of different opportunities, but I think the last bit here is really where we're planning on scaling. So by the mid 2028, our last thing is really trying to get to around 15 of these large municipal treatment systems and around 235 of our poly cartridge deployments. And that point, we'll be treating around 1 billion gallons of water per day. That's really when we're starting to get significant impact in removing microplastics at a global scale. And that's the ambition for our company. Cool. I think that's everything.
All right. That was a really exciting